So this particular, as you can see from the name of the problem given, this particular problem is actually known as, just a minute. This particular problem is actually known as transportation problem. Okay, because the term transportation is present over here. You have already got the hint that the problem is called transportation problem. So okay, fine. Then in this particular problem, the matrix is given to you, but you have to modify the matrix a bit further. This matrix needs a little bit of modification. So in the previous session, we talked about the capacity of the factories. The student asked about what the capacities are meant. I have put in the table, in the solution table, the capacities over here. You see, one extra column has been added. 40, 30, 50, all the capacities have been put over here. And the demand for the zones or destinations was also present in the given problem. Let us find it out whether it was indeed present or not. Yeah, you see, a company has 3 factories, say F1, F2, F3, that are feeding 5 zones: north, south, eastern, western, central, whose monthly demands are 20, 30, 25, 25, and 20,000. These are the demands. Demands mean what? Demands mean all these destinations, or these destinations, not this, you are actually a manager of a particular company, which you are actually responsible for the production. You look into the production management section of the company, and you have to identify that when the thing which is being produced in your company, where it goes, how it goes, what is the cost, what is the transportation cost, and where it is stored. Now, north zone, south zone, eastern zone, western zone, central zone, all zones have been marked. North zone, say for example, say Shambhajar. South zones, say Goria. Eastern zone, say Behala. Western zone, name it, I forgot. Central zone, say Shialda. Like this. In each zone, there are factories where these items which are produced in your factory can be stored. Okay, and what is the capacity of these zones? The factory which is situated in the north zone can intake 20,000, not more than that. The factory which is present in the south zone, the destination which is present in the south zone can intake 30,000 items, not more than that. The destination which is present in eastern zone can intake 25,000, not more than that. Western zone can intake 25,000, and central zone can intake 20,000, not more than that. So all these items are actually, all these things which are given in the question have been tabulated for the proper understanding. Here I have mentioned, what I have already told you in the previous session, I have mentioned over here. What is the, what did I say to you? I said what is 5? 5 is the cost associated with sending 1 unit of the item produced in factory F1 to the destination situated in the north zone. That is the unit cost. All these costs are unit costs. The question is, what is the total transportation cost and how to minimize this? What is the total transportation cost? To find the total transportation cost, we need to identify how many units of items produced in factory F1 need to be transported to the destination present in the zones, respective zones. So I am denoting this as, let small x11 units of the item be transported from the factory F1 to destination north. How many items? I don't know. Again, this x11 has now become a decision variable. I don't know what is the value of that. And in this way, xij means the item present in the ith row and jth column. In general, I have not mentioned everything, x11, x12, x13. So in general, I'm saying xij be the units of items which is to be transported from the ith factory. This may be any one of these 3 factories, ith factory to the destinations present in the node, each corresponding zones. So maybe may jth zone, okay, jth destination. So in this way, I have associated all the variables. I have associated variables corresponding to each of these cells. Okay, you see, if I do so, you can, by unitary method, you can easily identify the total transportation cost. Total transportation cost will be 5 into x11 plus 4 into x12 plus 7 into x13 and so on up to this. Don't include this part and that part. These are the restriction part. Okay, so the total transportation cost in this particular case will be represented by capital T, and we have got it, a long expression. The long expression can be made short, don't worry. The factory capacity, and here I have actually considered the standard form of the problem. Okay, I could have considered the general form also. I could have considered inequalities like lesser than inequality, greater than inequality. I intentionally considered the standard form. It is because if a particular problem is not in its standard form, we cannot solve it algebraically. You will gradually understand. Transportation problem is the second unit of your syllabus. So I shall discuss that thing in details over there. You can ask me one question, that if transportation problem is in there in the second unit, why are you discussing this right now? That will be answered, don't worry. So let me see this waiting room. Some people may be waiting over here. Okay, so you can ask me why you are discussing transportation problem right now. Do you want to finish the syllabus as early as possible? No. There are some reasons. I'm coming to that point. Now you see, if I consider the standard form, whenever I will find the values of the variables, like x11, x12, x13 like this, the destination constraints, means these constraints, 20,000, 30,000, 25,000, like this. These actually are nothing but, if we add the figures x11 for this, x21 for this, x31 for this, if we add this must equal to 20. If I add these figures like x12, x22 and x32, that must add to 30. If I add the figures x13, x23, x33, that must add to 25. If I add x14, x24, x34, that must add to 25. If I add x15, x25, x35, that must add to 20. These are called destination constraints. Similarly, there are some factory constraints. What are these? If we add the terms like x11, x plus x12, plus x13, plus x14, plus x15, that must add to 40. x21, x22, x23, x23, x24, x25, when added together, that must add to 30. x31 plus x32 plus x33 plus x34 plus x35, when added together, must add to 50. Okay, so these are called capacity constraints. These are called destination constraints. These are called capacity constraints. How many items are being produced? You were asking me how many items are being produced in the factory F1. X11, I'm saying 10 items. How many items are being produced in this cell? No items. In this cell, what is the value? 20. In this cell, no, nothing. In this cell, 10. Now you see, 10 plus 20 plus 10, 40. Okay, and you have to adjust all the figures in such a way so that this total, this total, this total, that total, that total, that total, they're all same. These are called the factory constraints and destination constraints. I have noted everything over here. I have discussed it already, and these things have been written properly, explicitly in this particular part. So I have got my constraints in its standard form because equality signs are already. You can ask me, sir, factory capacity means max to max you can produce 40,000. So can I write the addition of this must be less than or equal to 40? Yes, definitely. You can write less than or equal to 40, but I'm intentionally writing equal to sign because inequality like things have been already shown to you in sample problem 1. Nothing sort of equality have been shown to you. So after this class, you may take in in constraints only inequalities are present, not equalities. So that's why I'm actually showing you the standard form. But yeah, if we want to contain if you want to consider the inequalities in this particular cases, then that inequalities will be lesser than inequality. And destination constraints, what type of sort of inequality will be there in the destination constraint or warehouse capacity constraint? The destination in north zone cannot contain more than 20,000. Okay, that okay can also be uh, less than or equal to, or if I say the destination in north zone can contain minimum of 20,000 items, then that will be greater than or equal to. I have to specifically mention in the problem what I need to find. Okay, nothing is specifically mentioned in the problem, given problem. So therefore I didn't, actually I try to stick to the standard form of the given problem. And what will be the, and one extra thing, why I told you that this particular problem a little bit different from the previous one is because of this particular number. You see, the problem has been designed in such a way so that factory capacities are and destination capacities are exactly same, 120. Okay, and that will happen to each transportation problem. If this happens, if the factory capacity and the destination capacities are same, then the transportation problem is called the balanced transportation problem. Otherwise not. We shall be discussing that in details in unit 2. And lastly, since we are actually considering again the variables like how many number of items to be produced in the factories, these variables are again non-negative variables. These are not positive, negative variables. So non-negativity restrictions is also present over here. Combining each one of these, we can write our programming problem, the linear programming model as, since we are actually dealing with transportation cost now, so the word optimize will become minimize. And in short, that this big term like which I have written over here can be written in a concise form like this: C equal to double summation, one summation for the row and another summation for the column. How to play with the double summation? If we want to break it, what we first do is that we keep I fixed and we put all the j values. So we write Ci1 xi1 plus Ci2 xi2 plus Ci3 xi3 plus Ci4 xi4 plus Ci5 xi5. I's remain same. And then the summation I is acting over each of these i's. And we count from 1 to up to 3. If you break it, you will get the original one. So this is the way, in concise way, by which we can squeeze the transport for our own sake, for the purpose of not writing everything in details. This is the transportation cost which we need to minimize, subject to the restrictions. These restrictions have already been shown to you. And the non-negativity constraints are there. Xij's, the number of units produced in the factories, must be greater than or equal to 0. This symbol is called for all. This symbol, inverted A, is called for all. For all ij. For all ij means for all the cells. That is for all I 1 to 3 and j 1 2 3 4 5. And total capacity equal to total demand or equals to 120. That has to be mentioned. For the if you are dealing with a balanced transportation problem, that has to be maintained. Okay, total capacity must be equal to the total demand. This is the extra condition. This is the extra condition which we need to put it. And the general form of the sample problem 2 can then be represented like this. This is the final portion which I'm showing it to you right now. The general form can be shown like this. All the factories in general, in our problem there are only 3 factories. Now in general I'm showing you all the factories, all the M factories, F1, F2, F3, Fm, D1, D2, D3, Dn, all these are destinations. C11, C12, C13, C1N, all these are costs. X11, X12, X13, XMN, these are all the units or variables which we need to find out. A1, A2, A3, AM, these are the factory capacities. B1, B2, B3, Bn are the destination capacities, and summation AI must be equal to summation Bj. Okay, this is the tabular form of the transportation problem, and the mathematical form can be summarized as, the transportation model can be summarized as minimize transportation cost this. In general, previously it was from I equal to 1 to 3, j equals to 1 to 5. Now I'm writing it as I equals to 1 to m, j equals to 1 to n, and subject to summation j goes from 1 to n xij. That means the factory capacities for all i's, that will be equal to ai. You just break the summation, you will get the previous case. I goes from 1 to m xij equal to bj, that means the destination case for each j, xij greater than or equal to 0, and the balanced condition, that means total capacity of the factories must be equal to the total capacity of the destination. Entire thing together is called the transportation model of the transportation problem. And the most important part is that why am I showing this transportation model in today's class? Today's class was all about linear programming problem. Why am I showing transportation problem to you? The answer is transportation problem is a special case of linear programming problem. Why it is a special case of linear programming problem? In the induction class, I also told that if you want to know the transportation problem, then you need to know what is linear programming problem. That was the prerequisite. Chapter 2's prerequisite was chapter 1. Now, for that, keeping that in mind, I'm showing this to you. So what is that? You see, in linear programming problem, we need the objective function. So objective function is present. In linear programming problem, we need constraints. So constraints are present. In linear programming problem, we need non-negativity restriction. Non-negativity restriction is present. Extra condition is there. That can be. Linear programming problem doesn't didn't say ki extra conditions if available cannot be represented. Okay, so this is the extra condition. That's why it is transportation problem. Transportation problem has to be some sort of different from the general linear programming problem, isn't it? So this is the extra, which actually tells you that, yeah, you are actually dealing with a special type of linear programming problem. So students, this much for today's class. I hope you have understood. I am able to make you understand the basics of linear programming problem. In the next class, we shall start discussing how to solve the linear programming problem and what are the respective tools. Because if you can recall, we started with this particular problem, and this particular problem required actually two things: formulation, and then it actually asked how many units of each product should be sold to maximize. I haven't found in today's class how many units. That is the solution process. That is all about solving the problem. Okay, so in the next class we shall be discussing that particular portion. So here I'm going to end my today's presentation. And of the students have asked me that whether this condition is mandatory or not. If in transportation problem we need to have this criteria or not. Summation AI is equal to summation Bj always. Yeah, the answer is yes. But in practical, you may not get so. In some cases, you may get that in the total factory capacity is greater than the total destination capacity, or total factory capacity is less than the total destination capacity. In practical, it may so happen. In those cases, I shall term the transportation problem as the unbalanced transportation problem. But unbalanced transportation problem cannot be solved. We have to make them balanced by somehow. Somehow we have to make, there are tools, there are criteria, or there are some methodologies by which we can make a unbalanced thing balanced. When you take weights in the balance, okay, if one balance tilts, then what do? You put the balance, something, you take out or you put something so that it become balanced once again. So in transportation problem also, if the things are not balanced, there are some tools by which we can make it balanced. And if the thing is not balanced, then we cannot solve it. we cannot solve the transportation problem. Have you got my point?
Yes, sir.
Okay, I have seen that some other students have raised their hand. Okay, please ask.
Sir, I have a question. Actually, I said joined late. So, sir, if you explain the table one more time, I will be.
Which table? This table?
I mean,
This
sir,
one?
when you told us to, sir, when you end the meeting, you told us to summarize the problem. So, I missed that part when you start the
Okay, okay.
solving part of
Yeah, yes.
that
Solving.
question.
I didn't solve the problem. I actually solving of the any of the problems like sample problem 1 or sample problem 2 have not been discussed. Solution has not been discussed. Only this class was for formulation. Formulation have been discussed. So when I told that you just summarize this thing, by that I actually meant
Yes,
that whatever written here literally, you have to put it in a tabular form. So I have actually
yes, sir, yes, sir.
generalized.
From
Yeah,
that part.
actually I have generalized the table a little bit further. Everything which was there in the in this particular table is present over here in this table, but I have introduced one extra column and one extra row in this section. In the column, we have put the restrictions which were imposed upon the factories. What were the factory restrictions? Factory restrictions was that the factory F1, F2, F3, these factories can produce not more than 40, 30, and 50 items. So I have introduced, I have shown in the this particular table that yeah, the factory capacity of F1 is 40 in 1000 units, factory capacity of F2 is 30 in 1000 units, and factory capacity of F3 is 50 in 1000 units. Similarly, when in question it was told that the destination capacities of the north, south, and etc. and central zones are these, I have also included these values in the table to complete my chart. I have introduced the destination capacities. Those are actually known as demand. Demand cannot be for factories. Demand can be for warehouse or destinations. So I have put these figures over here also. North zone cannot take more than 20 items. South zone cannot take more than 30 items. Eastern zone cannot take more than 25 items, and so on. And if you want to solve the transportation problem, just now a girl asked me a question, Shumona, that whether this has to be always same or not. Yeah, it is required. For solving, it is required. If you want to solve the system, if you want to formulate this only, that can be different. The sum of these figures and sum of these figures may be different. One is greater than the other. But if you want to solve the system, then you have to somehow make them equal. I'm not going to tell you how. That will be discussed when we'll be discussing unit 2. But we have to make them equal. So here to solve the transportation problem, each time we have to check whether it is balanced or not. So I have specifically shown that here, the problem which I have considered here, the factory capacities are actually, total of the factory capacities are actually is same as the total of the destination capacities, which is 120. So that is the thing. And rest is just like what we, the rest, the remaining portion of the problem, that is the identification of the variables and the constraints, are similar to what we discussed in sample problem 1. So hope you have got your answer.
Yes, sir.
Okay, so can I finish my today's class? I shall be uploading the note in the Google Classroom.
Yes.
So if you have any doubt, after you go through the note, if you have any doubt regarding any portion, you can write in the comment section. I shall reply over there. Okay. So bye for now.
Okay,
See you in
sir.
the next class.
Okay, sir.
Okay. Okay.
Thank you, sir.
Thank you, sir.